Hi. So last time we talked about the idea that air is a mixture of gases, and we talked about the pressures like nitrogen at 78% and oxygen at 21%. But when we left off, we were talking about the idea that in order to understand how a gas moves from one place to another, we need to understand that in terms of pressure. Fluids, like gases, move according to pressure differences. So if I say that air is 78% nitrogen, I need a way to translate that into a pressure of nitrogen. So this brings us to the idea of partial pressures. To illustrate this, let's use this scenario. Let's imagine we have two containers of gas. So this is container A and container B. Container A is 100% pure nitrogen. And we're going to say that the overall pressure in this container is 800 millimeters of mercury. This other container, container B, will be 50% nitrogen and 50% oxygen. And its overall pressure will be 600 millimeters of mercury. We will connect these two chambers with a valve that when I open it, it will allow gases to move between the two containers. So when I open this valve, which way do you expect to see gas moving? If I had a little gauge here, would it be going this way as gas was moving that way, or this way as gas was moving that way? So when I look at this pressure difference, say gases move from high to low pressure, higher pressure on A, lower pressure on B, so I expect gases to be moving that way. And that is what I would see. If I open that valve, there'd be a flow of gases in that direction. But there's something about that that doesn't quite sit right. Because if I think about oxygen, there's oxygen here, but none here. So doesn't it seem like some of the oxygen should be moving that way? It does to me. Which means I have to think about a new way of looking at this. Rather than just overall pressure, I want to find a way to look at the partial pressure of each gas. So I want to look at the partial pressure for nitrogen. And fortunately, it works just about the way you think it should. If I wanted to know the partial pressure of nitrogen here, for the partial pressure of a gas, partial pressure of gas X is equal to the total pressure of the gas mixture. We'll call that partial pressure of X is equal to the pressure of the total mixture times the percentage of X in the mix. So for example, over here, the partial pressure of nitrogen is equal to the total pressure, 800, times the percentage of nitrogen, 100%. It's easiest if you're doing multiplications to represent percentages as a decimal. So we'd say Pn2 equals 800 times 1.0, which is the partial pressure of nitrogen is 800, which makes sense. The total pressure is 800, so since all of it is nitrogen, that's also nitrogen's partial pressure. But let's look over here. The partial pressure of nitrogen over here is equal to the total pressure, 600, times the percentage of nitrogen as a decimal, 50%, which is, in this case, 300 millimeters of mercury. And the partial pressure of oxygen is 600 times 50%, which is also 300 millimeters of mercury. So let's take a moment to list the partial pressures. So we're going to say that's a Pn2 of 800 Now let's look at each individual gas. Nitrogen has a higher pressure here than here, so nitrogen will tend to go this way. But oxygen has a higher pressure here than here, which means oxygen will tend to move this way. The pressure difference, the delta P for oxygen is 300, the delta P for nitrogen is 500. So there will be more gas moving this way than this way. But still, oxygen will be moving this way overall, nitrogen will be moving that way overall. And in the end, when this reaches equilibrium, we would expect them to distribute themselves about equally. This is a little bit like diffusion of solutes, where we looked at how each solute diffuses according to its own concentration gradient. There are some differences, but some of the same ideas apply here. So that's the basic idea of partial pressures. And what you need to be able to do from this is calculate the partial pressure of a gas in a mixture, and then talk about which way each individual gas in a mixture is going to go. So I'll put up a few problems here in just a moment on here so you can take a look at that. All right, hopefully that went okay. So now what I'd like you to do as an exercise is this. In dry air at sea level, the total atmospheric pressure is typically about 760 millimeters of mercury. I'd like you to figure out what the partial pressures for each of these gases are. All right, everyone managed to do it? Okay. And let's see the answer. And hopefully you got something like this. For each gas, it's the total pressure times the percentage of that gas in the mixture. These are the answers I get. Really, the only tricky one on this one is this last one. It's easy to forget that when you're multiplying by 0.04%, that's 0.0004. So if your answer came out something like 30.4, that's the mistake you made. That to make a percentage into a decimal, you move the decimal place over twice. So 78 becomes 0.78. 0.04 becomes 0.0004. All right, hopefully all of that went fine. If not, practice those a little more. You will need to be able to do that. So, partial pressures are relatively straightforward in gas mixtures. But when we're talking about how this works in the body, there's another wrinkle we're going to have to deal with. And that's the idea that these gases, once they get into the body, are not in the form of gases in a gas mixture, but they're gases in solution, dissolved into a liquid like blood. And that uses some slightly different concepts. So what we need to talk about now is the idea of partial pressure in solution. Okay, so let's imagine that I have a bucket of water and that water has no gases dissolved in it. Gases dissolved in water is just a matter of the molecules of the gas slipping in between the molecules of the water and just sort of hanging out in there. How long they stay and how easily they stay is an interesting question. We're going to get to that. So let's say we've got in the air up here a PO2 of 100 millimeters of mercury. So we'll represent that by some molecules of oxygen just bouncing around in the air up here. PO2 of 100. We start out with no gases dissolved in the water, so I'm putting no red oxygen molecules down here. Now, some of these oxygen molecules can happen to bounce into the water and slip their way between the water molecules and enter solution, become dissolved. Right at first there'll be none coming out because there's none in there. So we would say at first that oxygen overall is moving into the solution. So we'll move a couple of oxygen molecules in there. So now there's a little bit of oxygen dissolved in the water. Now that oxygen will start coming out as well. So in the next moment in time, the oxygen is still moving in, but now some is moving out. There's more moving in than out, so we'll add a few more. And at that point, it's starting to move out more. And at some point, pretty quickly here, we get to the point where oxygen is leaving the solution just as fast as it's entering. This may sound familiar to you. This is a concept we've talked about before. If we get to the point where oxygen is entering and leaving the solution at the same rate, you know that the amount of oxygen dissolved in the water is now constant. It's not getting bigger or smaller, and this is now equilibrium. So when this reaches equilibrium, our question is this: what is the partial pressure of oxygen in the solution? PO2 in solution. This one gets a little tricky. So here's the first way I'd like you to think of it. Imagine this wasn't water, this was just a gas. If oxygen was moving this way and that way at the same rate, and the PO2 here was 100, what would you say the PO2 in the other mixture would be if oxygen was moving back and forth at the same rate? If it's at equilibrium, it has to match this. So we would say the PO2 would be 100. For the same reason, when you're talking about gases in a liquid and they are at equilibrium with a gas outside of the liquid, then we say the PO2 in solution matches the PO2 of the gas mixture. So we would say this is a PO2 of 100 millimeters of mercury in solution. But there are some things to note about that. Number one, and I did this deliberately, notice that there aren't nearly, the oxygen molecules are not nearly as dense here as they are here. There's a lot less oxygen in this water than in the air out here. So having the same partial pressure in solution does not mean the same amount of oxygen or even the same concentration of oxygen. What it just means is that that oxygen is exiting the solution at the same rate that it's entering. It's at equilibrium with this gas. Another thing is that this is not actually a pressure. The oxygen in here is not exerting 100 millimeters of mercury of pressure on the walls of this bucket. It's really, think of it as the tendency of oxygen to leave the solution. This is, you could think of it as giving it a certain rate of entering the water. The partial pressure in solution is sort of its rate of leaving, expressed in the equivalent of a pressure outside. If that's a little confusing, don't worry. Partial pressures in solution are confusing. The take-home message is this. When you have a gas at a certain partial pressure outside of a solution, it will dissolve into the solution until we reach equilibrium. And when we reach equilibrium, we say the partial pressure of the oxygen in solution matches the partial pressure outside. Now here's a couple of things you can think about to kind of test your understanding of that. What would happen if I added a lot more oxygen here? Let's say I raise this to be 200. So some things for you to think about, and when I ask the question, pause for a moment. First of all, will this still be at equilibrium? If not, which way will the gas be moving? And once it reaches equilibrium, what will the PO2 in solution be? So pause. Okay. All right. First question. This is no longer at equilibrium. There's a lot more gas out here, which means there's more molecules entering the water than there were before, just by random movement. So let's represent that as this arrow being now bigger. So now more oxygen is entering the water. The more of it that comes in, the stronger the tendency to leave becomes, until it's at equilibrium again, with a little more oxygen in here. Now that it's at equilibrium, the partial pressure in solution is by definition matching the partial pressure outside. So when I raised this, it did move into solution until this reached equilibrium. Still not the same concentration, but there's more in solution now than there was. Okay, hopefully that makes some sense. Here's a real-world example for you to think about. Doesn't look much like a 2-liter soda bottle, but we'll say it is one. And we'll put our cap on it. Let's see. We'll make it grape soda. Why not? So. Bottle of grape soda. It's been capped. Now, when people bottled this, what they did is put a lot of carbon dioxide into it under pressure. So the PCO2 of this little gas mixture up here, I don't know exactly what it is, but I'm going to make up a number. Let's say it's 1,000. Now, if that is at equilibrium with this liquid, the PCO2 in solution should also be 1,000. What's the PCO2 of the air out here from what you saw before? Yeah, from our previously, that was about 0.3 millimeters of mercury. So when I uncap the soda, pop, so to speak, now I have these two gas mixtures. One has a PCO2 of 1,000, one has a PCO2 of 0.3. Which way is the CO2 going to move? Definitely, it's a huge pressure difference. So this CO2 comes out and mixes with the atmospheric air. After just a moment of that coming out, now what is the PCO2 here, just above the soda? Well, now it matches the atmosphere, so it should be about 0.3. Now, you might think, well, so doesn't this go up as that CO2 comes out? I suppose it does technically. However, compare the volume of the amount of gas above a soda under the cap to the Earth's atmosphere, and you'll realize that the amount of CO2 in there really does not change the amount of CO2 in the Earth's atmosphere at all. So it's reasonable to say this doesn't change, so this matches it. But now look at this. The PCO2 here is 0.3. The PCO2 in solution is 1,000. Which way will the carbon dioxide be moving? And definitely there's a huge pressure difference here. So much so that the CO2, if we were to draw that with those two arrows, we'd have a tiny, tiny movement inward and a very large movement outward. The CO2 in this solution is coming out rapidly. In fact, it comes out so rapidly that it can't wait to get out at just this little tiny bit of open liquid here, and instead forms bubbles. That's why the soda is fizzing. Those are bubbles of CO2 coming out of solution to form little gas bubbles of pure CO2 that is now coming up to the surface and releasing that carbon dioxide. It will continue to do this until this pressure difference is low enough that it can come out just at this surface, and then it will gradually reach equilibrium with the atmosphere. In other words, it goes flat. So, in terms of a couple of things about that, the famous Mentos Diet Coke reaction, where you drop a, if you haven't done this, don't do it without being careful. But if you open a Diet Coke and drop a Mentos into it, it will fizz very, very rapidly and suddenly and basically explode out of the container and get all over everything. So if you try it, do it outside, and do not open it up, put the Mentos in, and put the cap back on. The bottle will explode and it can hurt you. But what's happening there is not actually really a chemical reaction. As it turns out, the surface of the Mentos mint is ideally suited for forming these bubbles. So when you open a Diet Coke and put in the Mentos, those bubbles come out much more rapidly than they otherwise would. Effectively, you're helping that CO2 come out quickly, so it bubbles all at once, and afterwards it's mostly flat. Kind of an interesting thing. The other, though, is if anybody has scuba dived, you may be familiar with the concept of the bends, decompression sickness. So if I am scuba diving, when I'm underwater in scuba diving, I have to breathe air at the same pressure as the water around me in order for my lungs to be able to inflate. So if the pressure here pressing in on me is 1,000 millimeters of mercury, then the pressure of my air has to be 1,000 millimeters of mercury. And if that air is just regular atmospheric air, then that is still 78% nitrogen, so it has a PN2 of 780, which means as I breathe that nitrogen dissolves into my blood, and pretty soon my blood has a PN2 of 780. Which is fine. The nitrogen doesn't do anything to hurt me. And if I swim down deeper into the water, I'll be under higher pressure, let's say I swim down a little ways and I'm underwater with 2,000 millimeters of mercury. I'm breathing air at 2,000, which means the PN2 now is 1560. So my blood PN2 is now 1560. You get the idea. The more time I spend deep under the water, the more nitrogen dissolves into my blood. Again, not hurting me, although interesting things can happen when you get deep enough. The nitrogen does actually have a narcotic effect after a little while, but that's why one of the many reasons why you don't go scuba diving unless you know what you're doing. It is a fantastically fun thing to do. It is also one of the more ludicrously dangerous things you can do that's that much fun. I've done it. I enjoy it. Get trained if you're going to do it. Anyway, so let's say we spent a while down there and there's plenty of nitrogen in my blood. And then, let's say I come up to the surface quickly. When I come up to the surface, the PN2 of my atmospheric air, pressure of the air is 760. I think the PN2 is something like 593. Notice this. The pressure of nitrogen in my lungs is much lower than the pressure of nitrogen in my blood. So that nitrogen is going to start coming out of my blood. And if that pressure difference is big enough, I can run into the same thing that happened when I uncapped my soda. If there's enough nitrogen in my blood, and I come up to the surface without giving it any time to come out gradually, my blood can actually fizz. Nitrogen bubbles can form in my blood. Those bubbles can then accumulate in my joints and even my blood vessels, causing pain and even blocking blood flow and causing injury or technically death. It's called decompression sickness, or the bends, and it is one of the things that divers have to plan for very carefully. One thing you learn about when you're learning to scuba dive is planning for how long you're going to be at different depths, thinking about how much nitrogen is dissolving into your blood, and then as you come up, how you then come up gradually enough to let some of that nitrogen come out slowly rather than all at once. It's even important because if you go for a scuba diving vacation, spend some time down underwater, come up safely, everything's fine, and then get right on an airplane, suddenly that airplane, you're now pressurized as if you were at 8,000 feet of altitude. That can actually trigger fizzing in your blood as you suddenly go to a much lower compression as airplane cabins are pressurized. So these are all things you have to think about when scuba diving. Anyway, so that's the idea of partial pressure of some gases in blood. However, there's one more thing about this I want to talk about, which is that partial pressure in solution is even a little more complicated than that. So let's go back to our bucket. Go back to our gas mixture that had a PO2 of 100. And let's say we allow that to reach equilibrium. So I dissolve a little bit of oxygen in here, and I have a PO2 in solution of 100. So far, so good. Oxygen is at equilibrium. But now let's add another gas to this mixture. Carbon dioxide. Let's say we put enough carbon dioxide here to where we've got a PCO2 of 100. Now that should be represented by just about an equal number of carbon dioxide molecules as oxygen. The different molecules exert the same amount of pressure in a gas mixture. So if my PO2 is 100 and my PCO2 is 100, that means it's about 50% of each, oxygen and carbon dioxide. So when I add that CO2, it's now tending to enter the water. So CO2 starts to come in. But now here's the difference. Oxygen doesn't actually dissolve very well in water. It has a strong tendency to leave the water, which means that as just a little oxygen comes in, it builds up a tendency to get out quickly so that it will reach equilibrium. It'll match with just a little oxygen in there. Carbon dioxide is a lot more comfortable in water for reasons we'll talk about. Part of it is that while it's not polar, it has more electrical structure. Another is that it actually reacts with the water, as you learned about. So I can fit in more CO2 before it's at equilibrium. Once it's at equilibrium, the PCO2 in solution is still 100. So it's at equilibrium with this. But notice that while the PO2 and PCO2 in solution are the same, the amount of oxygen and carbon dioxide in solution, if you counted up those molecules, is not the same at all. There's more carbon dioxide in that solution than oxygen, even though they have the same partial pressure. That's because PCO2 has a higher, what we call solubility. For the same partial pressure, you can dissolve more CO2 in the water. That makes this a little difficult, because if I'm looking at a solution and I see the same partial pressure of oxygen and CO2, I cannot say that that represents the same amount of oxygen and CO2, because they have different solubilities. See, going from partial pressure in solution to concentration in solution is difficult, and it requires you to know the temperature of the solution, the solubility of the gas, and a lot of things. So, the take-home message here for us right now is this. If you see that blood has, for example, arterial blood generally has a PO2 of about 100 and a PCO2 of about 40. That does not mean that there's 2.5 times as much oxygen in that blood as CO2, because these two gases have different solubilities, and in blood it gets even more complicated. So you can't conclude from that which gas you have more of. What you can say is that we are then exchanging with air that has a PO2 of, say, 100. Let's imagine we were exchanging with air with a PO2 of 150 and a PCO2 of 30. I could, from this, conclude that oxygen will be moving from the air to the blood, because there's a higher PO2 in the air than the blood, and CO2 will be moving from the blood to the air, because there's a higher CO2 in the blood than the air. So I can use these PO2s and PCO2s to decide which way a gas is going to move, but I cannot really use the partial pressures in solution to judge which gas there's more of, not without a lot more info, and I am not going to ask you to do that. So, hopefully that helped. Partial pressure in solution can be a little bit weird, but this is the main idea. You're going to use it to determine which way gases are going to move from one place to another, and that's not too bad. Alrighty, I'll see you next time.